Take one. Hi, this is Atanu from Capsule Labs, and today we are going to take a look at how to create a composite graph from a comma separated value dataset using Microsoft Excel. This is an example of data visualization. Now, here I have some time series data collected from sensors in and around a 1,000-ton cold storage facility. As you can see, the data is in a comma separated value. So let's open up this file with Excel. We can tell Excel that the file has comma delimiters. So the strings between two delimiters are assigned to respective columns. This file would need to be pre-processed to eliminate the redundancy in the keys and make it easier to work with. A quick hack is to insert a new row at the top, copy over a row, and paste it with an offset. Now you can go ahead and delete the columns containing only the keys. We wrap the headers, and there, that's much easier to work with. Since this is a time series data, each row of the dataset can be uniquely identified using the day and timestamp values. Now, each of these columns is considered primary data because it was part of the original dataset. However, we may need to derive a secondary value from this primary dataset. For example, create a fancy time label for the timestamps by combining the day and timestamp columns respectively. In Excel, we have a concatenate function that allows us to join together two strings from column A and column B. Let's call this fancy time label. You can keep a small space in between. However, we notice that Excel has automatically recognized column B as a timestamp and converted it to a fractional number. To get around this, we can use the text function to convert it back to a string. We have to give it the format as well. Furthermore, we can use the left function to extract just the first few characters. That's more like what we wanted from the time label. Now, Excel has this very nifty feature where you can click on this little green box and expand the formula to the rest of the column. So that's a pretty neat way to create a secondary time label based on primary columns. Now let's say we want to plot the growth of inventory over time. That data is contained in column C. As a best practice, when creating a new visualization, we do not want to disturb the primary data set. So we create a new sheet. Let's rename that to inventory and copy over the inventory data column. Note that any change in the primary data set will not be reflected in this new data sheet. To avoid this, we link the inventory column instead of simply copying it. To link it, we say equal to, and then we copy over for the rest of the cells. Now any change in the primary data set will get reflected in this working sheet as well. We can convert this to a 2D line graph by choosing the line graph option from the insert menu. And there you have a line graph. In a line graph, the sequence or row number of the values are used in the x-axis. Although this visualization is correct, it is very difficult to interpret this because we cannot translate the x coordinate values back to a time frame. Therefore, we can associate some meaningful labels to this graph. For example, the fancy time labels we created earlier. Let's create a link to the column for the fancy time labels and link them to the computed labels in the previous sheet. We recreate the line graph, and tada, we have fancy labels in the x-axis that makes the visualization more meaningful and easier to interpret. Now in this data set, there are close to 3,000 data points, and if we plot all of them on the x-axis, the x-axis becomes unreadable. Now Excel automatically avoids that by avoiding printing more than 255 labels. But even that is a large number. So we can skip some labels by changing the number of the interval between uh, the labels, right? It is set to automatic, so it will scale up. But we can change this by specifying this to be, say, for example, 120. We'll leave it at automatic. Now note that all the inventory values are still being plotted on this graph. So there are 3,000, almost 3,000 points on this graph. But we observe that the inventory values is something that does not change very frequently. It changes in the order of hours and not in minutes or seconds. So therefore, we can downsample the data set to reduce processing overheads without sacrificing significant accuracy. The rows in the data set have minute level resolution. So let's create a secondary data set with a 1.5 hour resolution, right? And we can do that by sampling every 90th element. To create the secondary data set, let's create 3 column headers. We're just pasting the values instead of since it is the header value. Since row 1 comprises of headers, our first usable value is row 2. The next usable, the value that I expect after 1.5 hours is going to be 91, 181, and so on. To check if these are correct, we can use the index function on the labels or A column to validate that our samples are indeed 1.5 hours apart. First one is correct. The second one is coming in at 1 hour and 30 minutes. That is correct. Next one is at 3 hours. So that is correct. So this is a workable formula. Let's drag this selection till we have covered our data set. The last row returns 0 because it is out of range. And we can fix this by adjusting the index to the last value. In Excel, when we drag a cell containing a formula or copy it over, the references in the formulas also get translated. So when I drag the cells down, it changed the row number of the variable from D3 to D4 to D5 and so on. We can override the default behavior using the dollar formula to pin down the column or row or both. So let's go ahead and pin down the D column. This helps because when I drag it to the right, My formula becomes consistent and it has been applied on column B, but the index is being picked up from column D. Clicking the little green box populates the entire row for the secondary data set. Now we can go ahead and plot this downsampled data set that is much more manageable. If we just select the columns and plot the graph, Excel will assume that there is more data because we have 2880 rows in columns A and B. To avoid this, we must select the range we want to plot. There, that's much better. Let's plot it against the original data set and see how we have lost some resolution, but the structure is still consistent. However, this graph is still quantized because we took the 90th sample. It will look a lot smoother if we take the average inventory value from each interval. The graph will look a lot smoother if we take the average inventory value from each interval. The first row, we set it to 0 because there is no, that's the average value computed at this point. From the next row onwards, we can use the average function to compute the average over a range, but we have to specify the range. We do that using the index functions again. We specify the column on which this range is spaced and the first item in this range. Then we specify the second part of the range, which is again the same column B. And this time the closing element is indicated by item 92. There we have it. We have the average value. Since the bounds are inclusive, we add an offset to the first index in the range to prevent double counting. Expand it over the rest of the data set. If we plot the downsampled value and the average value on the same graph, we will find that the average curve follows the original curve but catches up to it. This is an easier graph to handle because there are no points of extreme inflection. Now, what if we wanted to plot the change in the average inventory levels over the intervals? We can do this by creating a new column to record the difference between current average and the average in the previous level. Let's call it change in average. The first one, of course, is 0. The next row onwards, it's the current average minus the previous average. And we extend it over the rest of the table. So let us go ahead and plot all three of them. However, if we plot these three curves on the graph, we find that the last parameter is almost invisible and just about hugging the x-axis. This is because the scale of the third curve is much smaller as compared to the other two curves. We can fix this by giving the third curve its own secondary axis. Converting the inventory and the average inventory to line graphs and the average to a clustered column. This kind of makes sure that we read the curves differently, and that is why we are using the column graph for this set of values. We can also change the scale of our axis to keep the focus on features of interest. And there you have it, a composite visualization of the data. At Capsule Labs, we organize data visualization camps at various institutions in order to develop a love for data science. Be sure to check that out.